Hello and welcome to another film about non-octet molecules. No, you haven't clicked on the same film twice. This is not the one about 5 charge centers. This is the one that deals with molecules with 6 charge centers, and hopefully by the end of it you'll know the names that we give to the different shapes that form when we have 6 charge centers around a central atom in a molecule. And once again we'll be able to make some kind of qualitative statements about the bond angles in these molecules. Right, we'll start with one that you need to remember. Okay, so you need to remember that both SF6 and PF6- are examples of an octahedral geometry. Now, if you draw the Lewis diagram, and like in the film before, I haven't been figuring out how you do these. I've been just assuming that you're still following the same rules that we had before, except because you're higher level, you're not getting too stressed about the fact that we've got more than 4 pairs of electrons around the central atom. If you drew one of these, you'd discover that whether this was a sulfur or a phosphorus in the middle of this molecule, and whether it had a negative charge or not, there'd be 6 pairs of electrons around the central atom. Okay, and the way that 6 pairs of electrons get as far away apart from each other as they possibly can is to form this octahedral geometry, which is a very, very symmetrical shape that it kind of always surprises me just how symmetrical it is, because these always look somehow different. These ones top and bottom always look somehow different to the others. These always seem somehow closer together than they do to those, but every one of these bond angles is exactly the same, and every one of the bond lengths is exactly the same, and in fact that's a 90-degree bond angle. Okay, so this is called an octahedral geometry. Right, so called because if you draw the solid shape that forms from these things, you get 4 faces on top. You've kind of got a pyramid with 4 faces showing, and 4 faces on the bottom. So altogether there's 8 faces, or it's a not a polygon but a polyhedron with 8 faces. So that's why it's called an octahedron. Anyway, leaving aside the maths, I suppose, for a minute. Here's something called a square pyramidal geometry. This is not one of the ones that you need to remember, but once again, if you were given the formula BRF5 or the name bromine pentafluoride, you could draw yourself one of these electron dot diagrams, not lose sleep over the fact that you've got more than 4 pairs around the central atom. We've still got 6 now, but now we've got 5 bonding pairs and 1 lone pair. Remember, it doesn't matter where that lone pair goes, because each of those 6 positions was entirely equivalent in the octahedral geometry. What we do know is that this lone pair repels the bonding pairs more than the bonding pair would have done if it was still there. And what this model, I think, is kind of showing is that this angle here is slightly less than 90 degrees. Okay? Because the lone pairs repel the bond pairs more than the bond pair would have done. Okay, so the sort of question you can get about this would be to draw the Lewis diagram, say what kind of bond angle you'd expect for this, and maybe compare that with SF6 or PF6- and say why it's smaller, and so then be able to make some statement about the repulsion between electron pairs. Here's another one that you have to remember, and this is the good news is it's the last one that you have to remember. And this is a square planar geometry, and you need to remember that xenon tetrafluoride is an example of this. Now, a little bit more subtle here, I suppose. If we draw the Lewis diagram, and again we end up with 6 pairs around the central atom, we could say that in order to minimize the repulsion between each other, the lone pairs would be best off at 180 degrees apart rather than being 90 degrees apart. Okay, remember, it doesn't matter to which of these 3 axes they go to, but the lone pairs have to be 180 degrees apart if they're going to minimize their repulsion. What this means is, and here are my lone pairs, what this means is that they will be repelling, this lone pair will be repelling these bonding pairs upwards more than the bonding pair would have done, but this lone pair is doing the same downwards, and they'd cancel one another out. So you'd be left with bond angles in here that would still be exactly 90 degrees. Okay, and this would be called square planar because we're forming a square of atoms that are all in one plane. They all lie on exactly the same plane. So I could draw this molecule perfectly flat on the page and it would be realistic. So that's it. That's the good news. There's only 3 of those molecules that we're looking at, or 3 of those shapes with 6 charge centers. Hopefully those names will stick. You need to find a way of remembering them, and you need to also find a way of remembering the specific examples of square planar and octahedral. And if it wasn't making sense before, then hopefully it's starting to make a bit more sense now, how we can make these qualitative statements about what happens to the size of bond angles if we start swapping lone pairs for bond pairs and vice versa. Okay, as usual, any comments or questions, most welcome. Please post them on YouTube because that way other people get to see them as well. But if you'd rather come and see me, then do that.